So today I will continue the Fortran lecture, and I will also at the end also go through some of the techniques for building and maintaining your software project or Fortran software project. But first, there was a part I missed on variables in Fortran last time and subroutines. There is a notion of something called automatic variables. And these are variables that are created, temporary variables in subroutines. They're created on the stack and then automatically allocated to the desired size. They must fit in the stack to be able to use. So, and also, perhaps we should have a distinction here. There are two kinds of memory in most compiled languages. Things that are creating on a stack, those are typically the variables you declare in a subroutine are allocated, scalars for example, are allocated on something called a stack. You can also create arrays dynamically on something called a heap. And stack variables are handled automatically by the compiler and the generated code, but the heap allocation is always allocated through the operating system. And heap allocated memory is much slower than on the stack. So just illustrate what this means. So I have here a program. I have an array here with the dimensions 20 by 30. This is a stack variable. It's allocated on the stack when the program starts. So it's a predefined memory area that is defined at program startup. And then it's maintained, it's there all the time. And then I call my subroutine, I pass my array over to the subroutine. And you can see here, I have my subroutine here, A, in my contain section of the program. I can declare it by colon, comma, colon. And then I can declare another variable that has the size of A. So size A1, that is the columns, the rows of A and the columns of A. So B here is allocated automatically for us on the stack, and you can use that in your subroutine. But after the subroutine is done, that variable goes away. So it's automatically allocated and also automatically disposed of. And it's not dynamic memory. It's not allocated on the heap, but allocated on the stack. So it's if you need something temporary, you could consider this instead of using a dynamic memory allocation. So coming to arrays here, so now I will go through some of the array features that are built into Fortran. So up until now we have looked at arrays at statically sized at when in your source code, but it's not always that you can determine the size of an array at compile time. Perhaps you have an application that can handle differently large size problems. Then you need to kind of be able to allocate memory on the fly at runtime. And you can declare allocatable arrays by adding the allocatable attribute to your variable declarations. You only define the ranks of the arrays in your declaration, so you don't give them explicit size, you just gave them the number of dimensions you want. You create the array using the allocate statement. And perhaps you have heard it before, but in many of the older codes, you created a system where you could do a similar thing here, where you allocated at compile time a really large array, fixed array, and then you had your own subroutines for managing that work array. Because Fortran 77 didn't have the ability to dynamically allocate memory. When you are done with your array, you deallocate using a deallocate statement. And if you have an allocatable array inside a subroutine, it's automatically deallocated. I think Fortran 90 didn't have it like this, but Fortran 95 added this feature. So it's a nice feature to know that when you have allocated something in your subroutine and you don't use a return, that is automatically deallocated. So how does it look? So this is the typical declaration here. Real dimension colon, so you just specify the colon here, that is the dimension of the array, and then you have a two-dimensional, you have colon, comma, colon, and then you have this attribute here, allocatable, and then the name of the variable. Before you can use these variables, you need to create the memory or ask the operating system for the memory. So you call allocate, and then here you give the size of your array. And that doesn't need to be a fixed number here. You can have a variable. So you could have, for example, allocate fn, or rows, comma, columns here. So this can be programmatically controlled. And when you're done, you need to deallocate here. So you have to kind of keep track on how many allocates you do and how many deallocates you do. Because if you, for example, are running in a loop and you're continuously allocating things, but you're not deallocating, your program will fill the memory of your computer, and at some point, either the operating system will crash or your program will crash. It's probably your program first. So what you can also do in Fortran is that you can extract arrays from other arrays. And you can also extract a slice from an array and give that as a parameter into a subroutine call. And if you're familiar with MATLAB, this is very similar to what you can do in MATLAB. So here you can see here I have an array here, 5 by 10. I fill that with numbers just like this. Ignore this. It just fills it with numbers from 1 to 50. And if you write the entire array here, you can see here it prints it out like this. But you can also do 1, 5 times 10. And now the array becomes a vector. And then you can have a sub-array, 1:5 to 5:10. That is a sub-array. And you can see you can put it out in different ways here. You can also give it indexes. It's a bit cumbersome syntax here, but you can do a parenthesis /1,3 /parenthesis, and that will also be a sub-array inside, which you can pass along to a subroutine. You have to be aware that this is, if the compiler can't kind of extract them in a way that you can pass along, there will be copies made. So the compiler will kind of see if it's possible to pass it just like a pointer. Otherwise, it will create a temporary object. So you have to be a bit careful how you use this here. It's no problem if you just do write A like this, no problem. And also if you go in a way that it's with single, so you don't have a stride between them. But it's useful to have this ability to index and slice arrays in different ways. You can also do matrix multiplication. There is a matmul function here, because you know that the multiplication operator is not matrix multiplication, that is element-wise multiplication. So matmul is a way that you can multiply arrays together. There is also a scalar product here called dot product, where you also can call. The important thing here is, compared to, for example, NumPy, is that you really need to make sure that the declarations are matches, because there is no checking being done here. You can have some warning in the compiler, but if your arrays don't fit and you try to call matmul and the C is not, you will get a memory error. So, for example, here I have 3 matrices here. I just fill them with random stuff. And you can see here that C here is 4 by 8, and A is 4 by 4 and 4 by 8. So you can see that they conform, and you can see is the correct size. So you need to kind of figure out the array sizes here, because there is nobody else doing it. So it's not as flexible as NumPy. but it's still useful. There are also routines that you can call on arrays. So, for example, all return true if all elements are true. Any, if any element is true. You can call max val, min val on an array, and then it will calculate that. Product of all elements in the field, sum of all elements in the field. So you can see here that those all work on arrays, and you will get max and min values, the max sum, and the max product.
So the all on the previous slide, the all and any.
Yeah.
They take
the logic. Yeah.
This we were talking a lot about arrays, and then
yeah.
You don't feed.
But you can have a logic array, and then
that will be handled. So you can feed in a logic array.
Yeah.
Work if all elements are true, for example.
Yep. Yes. And there are some other informational routines here as well, like lower bound, upper bound, shape, and size. Size we already covered here before. So that is kind of what you have in array functions. It's not like NumPy, but it still has a lot of built-in things for handling arrays. Input and output. We haven't covered that as much. So reading and writing for files, you use the read and write statements. And in Fortran, each read and write statement is considered, if you're reading text files, it's one row. The first parameter of the read statement determines where you read from or you write to. And if you put a star in the first, it will use either standard output and standard input, basically from the terminal console. And also, Fortran will automatically convert the text in your text file into the variables you're reading in. So you don't have to do the string or float things here. It will automatically do that for you. And also you can read several variables in the single statement using a comma-separated list of variables. And you can also have something called an implicit loop inside your read statement or write statement to read several items at the same time with a loop variable. So for example, what I mean here is that here I read from standard input. And the second parameter here we are not using currently, but that is the formatting. And then you just give your variables that you want to read as a comma-separated list. And that will look for the values in the text file, and the value should be separated with a space. You can also do, if you have this here, you can compress this to something like this. So I equals to 1.8. It's similar to what you can do in Python with lists. And of course you can do it the other way around. Here you have write here, that is standard output, so that will be on the screen. And you have a loop inside here. If you only want to print to the terminal, just like normal print in Python, you can use the print star comma, and then you can do so print star and then the text directly like that. And of course, as in Python, you need to often format your output from your application in certain ways. And the second parameter in the write statement, that is a format string. And star is the kind of default, and that will print all floating points with the maximum precision. So it will be really long numbers with an exponential afterwards. And so if you want to print nice reports, you can't really use that. You need to kind of put the formatting string in that second parameter. And you give the formatting in certain codes. It's very similar to what you did in Python. So you have n, that is a character string with a width of n. In, that is an integer with a width of n. And then you have j, floating variable with a width and n, m, width and n decimals. So you can also in your formatting string, you can say that I will output 6 values of the same type, and then you do put a number before, so 6i5 here. So that means that I will output 6 integers with a width of 5. And the formatting is always, it's a bit kind of odd, but you have the string delimiter here, and then you have always a parenthesis in the string, and you have an end parenthesis in the string. So here you can see how it looks. You have here, I have A is an array of floating points, B is an array of integers, and I want to print out, first I print the header here. So 3A8, that means that I have 3 strings that have the width of 8, followed by 4 strings with a width of 5. So you can see here, this is 8, and these are 5. So that can be the header of the table. And then I have here, I loop over the arrays here, and I have 3G8.3. That means that 3 floating point values with 8 decimal, let's see, with the width of 8 and 3 decimal places, and then I followed by 4 integer with width of 5. So if I run this, you can see here that I get the columns are sorted here. This is 8, next one starts here, and so on. You can see also that I have 3 places here, 3 by 3 here, and if I increase this number here to 4, now I will see that the formatting will be okay. Now, so if it can't solve the formatting, it will print stars. So if I give it a bit more width here, it should work. Now you see here I have 4 places of accuracy. But now you see the formatting above here doesn't work, so I have to add 2 ones here and 2 here. Then they should be.
Did you need to update the EA?
Yeah, sorry, yeah, 10. Didn't it compile? 3A10, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Two, 3, 4, 5, 6, 7, 8, 9, 10. It still seems to be 1 off. I'm a bit.
The numbers are implemented in the output.
How do you know there's a mistake?
Sorry?
How do you know there's an error? Those things?
Return 0 here, compiler return. So it compiles automatically. So if I put X here, it should be an X in the beginning here. If I, yeah, no, but. But if I go back again, let's see here.
Now the numerical values are not incremented by 1 step again. It would have lined up before.
Yeah.
I'm not sure where that incrementation comes from.
If I do. That works. And if I do. That works.
Your numbers had too great of a width, so it added some white space. That's why it didn't line up.
And now it then was add. So I have 8 now. 1, 2, 3, 4.
That will fill it up. But the numbers have some white spaces locally.
Yeah.
Because they have width of 12 in complement. Position over there.
And that was kind of not useful. 3, 5, 6, 7, 8, 9, 10, 11, 12. It seems like they are centered here somehow. These are aligned correctly here.
If you decrease the, what do you call it, width of the flows,
Yeah.
so it will get rid of some width on the numbers.
Yeah, but then you get. I think that it's correct with the spacing here. They are spaced exactly the same, but it's centered in mid. Okay, but you have to experiment with it. But the idea is that you have 3, and then you have the width for the field, and then the number of numbers here in the representation here. So, okay. But sometimes you because you have to put the formatting code in a string. Sometimes, for example, if you write an array printing routine, and you want it to be able to handle different kinds of different sizes of arrays, you can't have a single. You need to put the number 10 between if you have 10 columns. And you can't put variables in the formatting strings, so you need to kind of figure out a way that you can create this dynamically. And that is something I call dynamic format codes. That's not part of the Fortran standard, it's just a tip on how you can do this in Fortran. So you can create a format code that can handle dynamic number of values because you have to put that into a single string in write. But what we can do is that you can actually use character strings in Fortran as files. So what you can do then, I have a character field here, 255 with a formatting code that should contain my formatting code. I have my rows and columns here from my array here. And then I write have this as instead of the standard output, I put my character string here. I put my formatting code here, and then I write out a string, A, columns here, A1, and then 8.3 here. And then I put my print formatting statement here, either in a print statement or in a write statement. But there is something not working with this one. This only works up until you have, if you have 10 columns, it doesn't work anymore. Because you have this I1. So if you want to make this completely dynamic, you need to have if statements here, how many positions you have in your integer. So you have to have I2 here, or I3, I4. But this is the idea that you can create them dynamically by writing to a string and then using that string as the format code. The next up now we have been able to write to standard output, so to the terminal or to the screen, but you can also write to files, of course, and read from files. And it's similar to what you do in Python. You use the open statement to connect a file to a token that you can use to, or when you write, you can tell the write statement where to write. And also the open statement, you tell your program where to write. So it can either you tell it to read or write or append to a file. And that you do using the open statement. And there are 3 modes of operations you can do in Fortran. You can have text files. You can have something called namelist.io. It's very similar to JSON file, but not as nice. Unformatted I/O, that is binary files. So you can take your arrays and write them as binary directly to disk. Same with Python. When you're done writing, you need to close the files. So tell the operating system, I'm done with this file, and I can continue on working with my, or tell the operating system, it's free for you to do to write it down to disk now. You don't have to cache it anymore. So here's an example. What I usually do is that I define 2 constants in my code, or multiple constants for the files I want to use. So I have an integer parameter in file. That is the file I want to read. I have a integer parameter out file, and I give them numbers. That's you can give them any numbers except 5 and 6, because 5 is, let's see here, either standard input or standard output. Some of them. So those are pre-defined numbers in Fortran that are connected to the standard output and standard input. But any other number will work. So I have 15, 16 here. Then you do open, and unit is the name. So it's a kind of, in Fortran you don't have a file object, but you associate the file name with the number. So in file here is 15. So open unit 15. This is the file name. This is how you want to access it. Sequential, that is text file based. And then what operations you want to do. So action read. So this is like a Python. You have the file name and you have the read R string. That is very similar here. But you don't get an object back. So you need to remember that you use the in file here for reading now. And then you give the in file constant here as the input to the read statement. And the read statement will know that it should read from this in data.dot file name. And then when you're done, you just close in file, open unit out file, and then you have access sequential, but you have action write here instead. And then you write to the out file here, and you close your file. So not too different from Python. And you can read from keyboard as well. So read star star, that is from the keyboard, but 5 is the predefined unit number for keyboard. And the file is, you define a unit name, and then you read from that one. Writing to the screen is star star. The unit number 6 is the default for standard output. Yeah, I will show you that before. So that was a bit about reading and writing files. Then I want to go into code structuring. So building larger files in applications in Fortran. So a smaller project, modularization usually is not necessary. If you have that covers a couple of pages in source code, you can keep it in a single file. But if your project grows larger, you need to kind of maintain the code in a certain way, in a way that you can go back to it and update it. And in modern Fortran, the key to modularization is the module. And we already showed you how you define modules. And the idea with modules is that you should group related subroutines and data in logical modules, just like we did in Python. Some examples here. My main program has 4 modules, or 5. Input data, finite element, solve for solving, the solver, output data for writing output data. And then I have a common module here called utils, which has some shared, either it can be constants or data types that are shared among all the other modules. And then you kind of use them like this. So you have here, my main program here has, we tell it to use input data, output data, fem, and solve. So here I have all the things I want to do to control the flow of my program. And then you have fem that uses the utils module here, and utils modules here. It could be some things like print matrix, print vector, and so on. And then here you have the finite element elements, for example. So utils is something that you want to share between all of them. And I can show you an example of this here. I have my So I have this finite element code here, really simple. It consists of two files here, main and module truss. If we look at module truss here, you can see here I have this also uses some modules here. These are common to the source code you have seen here. So there's one module here for data types, one module for printing things, stuff like that. And then here I have my own module subroutines in this module here. And then the main program here also uses utils and data types, but also uses the truss module. And this is the same thing as using import. So these routines here, bar3e and print matrix, will be available to me from these imports, or these use statements here. See if I run this here. You can see here, this routine here, print matrix here, is contained in my utils routine, and it formats the output here. And we can actually look at that because that also uses the print matrix here. You can see here I have format here. I have some if statement here to control I1, I2, I3. And some other things here to print it out in different ways here. So I don't have to think about how I print matrices. It can also print the name of the matrix and the size of the matrix here, which data type it is. So you can see here that this is a print matrix D that is for double precision. This is how you can kind of combine that together.
Module overloading or whatever you would call it. Like if a module that you import or use uses modules that you already know.
You can't. Yeah, you have to have unique names of your function subroutines. Otherwise, they will clash if you use them. But you can do overloading of. So actually, I can show you here how it's done in this. So you can see here when I in my main routine I use print matrix. I didn't have the _d. But in my utils here, if you look here, I have print matrix here. I can actually define which subroutines it will look for if I provide my different data types to my calls. The compiler will choose from me either print matrix D or print matrix S. So if I go down here, I have print matrix D, so that is real DP. And then I have another one here, print matrix single precision, real SP. So when I call print matrix, it will check which data types I will call it with, and then call the correct of these methods. And that is also how it actually displays the, let's see here, I have the double, you have single precision here. That is printed because it's called from that routine. So if I go into my main program here and now I don't have that, let's see if I do like this. Yeah, now I defined it with different, that it will be garbage here, but you can see it called single precision here. But I initialized it with double precision here. That's why it didn't work so well. But anyway, you can use overloading like this in Fortran as well. And you use that by specifying the interfaces here. So I have print vector, same thing. I have two methods here, which is called depending on the data types that are being used. So it's a bit about like generic programming in C++. You can achieve the same things by having overloading like this. Yeah.
Just for curiosity, and what is the difference between single and double?
So single precision is only 4 bytes, so the floating point value is represented by only four bytes, and double precision is usually 8 bytes. So it's the precision. So a single precision can't represent as accurate as double precision. But it's sometimes operations can be quicker with single precision, a lot quicker, especially with GPUs and stuff like that. But double precision, both of them are supported by the processor. But if you have 8 bytes, it's a larger data type. It takes longer to calculate. So a bit more about subroutines. You can give other procedures or subroutines as arguments to your subroutines. The thing that you need to kind of make sure is that the subroutine you define is the same number of arguments and also the same kind of data types. And you declare the procedure type in the specification part of your code. You can't use internal procedures. So this is a bit complicated here now, but so I have a routine here I call tabulate. It's similar what you did in Python here, but I want the function to be able to start, end, and a step, and then I want to give it a generic function to tabulate. And here you can see I defined the data type of the function, so to speak. So again, interface and interface. And here I say I expect a function with real 8, and it should also, the x should also be of real 8. I should have put dp here. I don't know why I have. Yeah. And then I have in my module. I also have my own function to this, so I can define any function here in my module section. And this is what I want to call the tabulate with. You can have multiple functions here, and it should correspond to the same declaration as here. And then you can call tabulate with this function here. And that function could be located somewhere else as well. You can have multiple functions that you want to call, and it will be called here. And you can select different functions here. So you can do the same thing as you do in Python. In Python, it's very easy to kind of pass a function. You just declare it as any parameter that you have. In Fortran, you need to be a bit more explicit and declare your function, the type, how the function should look like. So you can't give it any type of function. It has to be the same number of parameters that you have defined in your interface here. It looks something like that. Another thing that you can do, which is very similar to what you do in Python, is that you can give your arguments keywords. And you can also have optional arguments. So one thing that you can kind of notice when you start coding in Fortran is that your subroutines argument list grows. You have a lot of them all of a sudden. And what you can do is if you know that many of these arguments always have some kind of default values, you can define them in your subroutine declaration, and you can declare them as optional. And then you don't have to pass them when you call the subroutine. You call them with the arguments that are required, that is not optional, and you can leave the optional out. What you need to do when you have a subroutine with optional argument is that you need to kind of check if an optional argument is given or not. And you do that with the present function. And also all the arguments in Fortran, you always see it when you did open here, you do open unit equals. That is a keyword argument. And that is something you can do in modern Fortran as well. So for example, here I have a subroutine for ordering ice cream, which is probably very common in Fortran. So you have 3 arguments. You have number, flavor, and topping. And you can see the number here doesn't have any optional arguments, so that is a required argument. But you always have to call it with that. You can't leave that out. Flavor and topping, however, are optional arguments. And if you want to check in your code if the user has given a certain argument, you can check here, if present flavor. And then if that is true, it will print out. Otherwise, the flavor argument was not given. Same thing with present topping. And you can also check of that. And then you can call this in different ways. So you can call it order ice cream with 2. That will be, because that is required, so you can't call it with less arguments. And then present here will be false. Both of these here will be false. Then you can call it with 2 arguments, then it's number and flavor given. And then you can give it 4, 4, 2. And then that is the normal way of calling a subroutine. But suppose you don't want to give the flavor, but you will want to give the topping. Then you actually need to give the keyword argument for give the keyword for the argument here in this case. So 4, that is the number. Topping, that is the third argument here. And flavor is not given. But you need to be able to do that, you need to give which argument you want to give. You can do that for everybody. You can have number equals 4, flavor equals to 4, and topping equals to 3. So you can give keyword arguments to all of them. And that makes it easy to use the same subroutine, but you can give the option of having one that is really easy to use, one that is a little bit more, and you have the same code here. You don't have to change the code. You can just check if that argument is given or not, and then act accordingly. You can also have, for example, the default flavor being a certain value when you start up the routine here. Overloading, I already almost showed that. You can define procedure calls to different procedure depending on the data types. You can declare, as I said, with the print matrix, and depending on what you call that subroutine with, it will call the correct one depending on data type. So what you do is then you declare an interface, and you give the subroutines that will handle the different data types. So here, for example, here I have a module. I have 2 variables here, 42 and 42.0 here. So this is a floating point, this is an integer. And I want to create a single function that I can call both that will call a certain data function depending on the data type here. But the user shouldn't know about that. It should be transparent to the user. So the first thing I will do, I implement my functions just like normally. So I have one integer function for handling the integer operation, one function for handling the floating point operation, and I give them different names here. So I function, R function. And then I create a interface here with the name I want to be able to use as common for these operations. And then I do module procedure, ifunc, rfunc. So then the compiler will choose the correct one depending on the data type. So it's not handled dynamically, it's depending on the compiler will choose the correct version of it. Yeah.
The position on the DP is set by DP?
It's set in the special unit here, not shown. So I probably have a, I'm not sure here. I haven't, there is some missing here in the code.
Okay.
Yeah. But assume there is a constant called DP. And it's used by the module as well. So there should be use my data types or something.
In that case, it would have been.
Yeah. So DP here is just, it's available. But it could have been real 8 or it could be something else. Yeah.
Can I ask?
Yeah.
What's intent?
Intent. That is something. It's an optional thing that you can give to the variable, and that means that this argument is not supposed to be modified in the subroutine. So it's going in but not out. So there is an intent out as well. So if you have a variable argument variable that you want to kind of assign in the subroutine, you can give it intent out. And that the compiler will enforce this. So it will check if you do an assignment and it's only in, it will not compile. So it's a additional safety to make sure that you don't modify something that you shouldn't modify.
But it's courtesy, right?
Sorry?
So it's courtesy coding to create a constant or whatever. Right? Because the compiler will react.
Yeah, it will check that X here is not overwritten. Yeah. Or you just don't try to assign to the X variable. So if you remove that, it still works. But now there is no check for overwriting. So it's a good practice to always use intent in and out. And it will be a lot of beneficial when we come to mixed language programming, because when you want to try to convert this using special tools, these tools will look at intent in and out to handle the different variables going in and out to the Python module in different ways. So it's a good idea just also for the code to be more robust to have that. Yeah, and you can use for operations on derived data types. So if you want to implement vector or matrix operations, you can do this using this operator overloading. You can also create overload operators, just like you can do in C++, for example. And then you define which functions to handle this operation. So you have type, derived data type, function name, operand 1 and 2. So if you want to have a function that implements matrix multiplication using a certain operator, you can do that. And then you give it a name that will do the operation, and then you give it in the interface declaration here. So this is how you can do it. Now I have the DP here. So you have a vector that has a real component with 3 components in it. And I can define operator plus here. And then I need to tell Fortran which subroutine to call when I use the operator plus here for my vectors. So here you can see I have type vector, vector plus vector, v1, v2, and then I do my vector addition here. And that's it. So now I have redefined plus for the vector data type. So you can see it will use vector here, and when you have an expression of that, you can use, it will call this routine here. So you can see here, I used my vector operations, I declared 3 vectors, and I assign them here, and then I can do this.
Well, what's the default behavior of this operator or whatever? It's still going to be there somehow?
No. So because all of these are vectors, type vector,
yeah.
It will only call this subroutine that I do, because I redefined plus.
Right. So right now you can't add 2 doubles together.
No.
But, okay. Then I understand it.
But if you would have called minus here, it will call the default. So, but the important thing is that you can redefine them, and that enables you also to do. You can define your own algebra for different data types. So it's good to know, and there's a lot of uses for it.
But I probably should have alternative ways of handling that if I also want to add integers together.
Yeah.
I should handle that explicitly.
Yeah, but in this case, because I have my own data type, it will not override anything else.
Yeah, in this example, right?
Yeah.
I'm probably going to mix data types in programs.
Yeah, and then it can be complicated.
Yeah.
Then you need to, if you go back here, then you have to define operations for different things. So you probably have the vector plus scalar plus vector. So you have to define all those to kind of so that the compiler can match the correct subroutine.
And can I be nice to myself and sort of call the native functions for normal cases of plus?
I haven't tried.
Or would this be very complicated?
I don't know what if it encounters a type vector plus something that is a native data type. I'm not really 100% sure what it will do.
We'll just do reals.
Yeah. We could. I don't have time to try it out, but yeah.
But this is a way of redefining it, but it will it will redefine the symbol.
Yes.
Completely.
For those the operations. So in this case, it will redefine type vector plus type vector, nothing else. So if you have some other operation, I think it will you get the compiler error, because if you have type vector plus 1, it doesn't know what to do. So you need to define all of those if you want to have a complete algebra for that.
Yeah. But real plus real. We define plus.
And then the result should be vector. So you need to define all the functions that kind of, all the combinations of the types, or the operations you want to do with the different data types. So it can be, I would say, complicated to do it for, that it covers all situations.
And does the name matter?
The name of the
Function?
No.
You can call it whatever.
Yeah, so I did print matrix underscore D in my print matrix unit. And I print matrix underscore S. That's my invention. And the compiler will figure out and try to see if we can find a function that matches. Yeah?
But this is an example, right?
Sorry?
This is an example. I mean, if we don't define vector plus vector,
Yeah.
and we use the operator plus to calculate a new vector,
Yeah.
is it going to is Fortran going to calculate the vector v without defining the?
And that's a bit uncertain how it will. I think it will. If and we can see if I can just take this. I think I have this in my. So I can try here if I just do underscore dp here. Let's see if it compiles. No, because it couldn't figure out the other data type. So you need to define the operation for vector plus real as well. So I think if you do go in here and define another function here, type vector plus real. So you need to kind of make sure that you can handle all the cases. Another thing you can do in your modules is you can control the visibility of things. Because sometimes you implement a large library of things and there are certain routines that you don't want to expose the users to. These are my internal subroutines that I don't want to kind of everybody to use. Perhaps I want to change them at some point. And then you can use the private and public attributes in your module. And you can do that by using the private, and then you can tell which subroutines or you want to expose. And you can also have a public attribute on global variables, for example, in your module. So here I have two variables here, integer public visible. That variable will be visible to anyone using my module. And that is the default. So by default, everything is public. So you only have to kind of declare a special if you want to have something private. So for example, integer private invisible. This variable is not visible to the user of my module. The linking will fail. So you can't link them together if you try to use that. If you want functions to be private, you do private and then the name of the function, public function. Also, the default is all subroutines and functions are public. So for example here, use my module, I want to call the private function here. Now you can see what happens here if I compile. You can actually, it won't even link because this is not visible for the linker. So that's one way actually, so you can really protect your subroutines from being called by mistake. So this will work because this is a public function. Also, I will go briefly over pointers. You can read more yourself here. We will not use pointers too much in this course. And pointers are very different from C and C++. So pointer is a reference to a variable. It's strictly typed, and everything that you want to point to needs to have a target attribute. So you need to, if your variable should be able to be pointed to, you need to kind of add a target attribute to that variable. And now it can enable you to return allocatable arrays from procedures, which kind of is something that has changed now, because you can, in the latest Fortran, do that anyway. But if you don't use a pointer, you use the nullify pointer statement. So you don't go in and say that pointer is equal to 0. You use nullify pointer to disconnect the pointer from a target. And you use the equal sign, greater than sign, to associate the pointer with the target. So that is the kind of assignment. You don't use the normal equal sign assignment. You use this to point to a target. So here I have an allocatable array, A, and I have a two-dimensional array with an attribute pointer to B and C. So B and C are pointers, and A is a target. So you can't point to anything else than A. So I allocate A. I say B points to A. And now you can use B just like would be in A. So you can query the size. You can also create an array here inside this here and get the array out. You can query C just like you query A. You can deallocate here, which you have to do because this is allocated here and continues using here. And then if you're done with using a pointer, you can do B points to null, or you can do nullify B. That's the same thing. But what you should be careful with is this statement here. B11 equals to 0, or something else. Because B doesn't point to anything now. It's kind of empty, and it will crash the program with a memory fault. So this was the argument for using pointers before. Sometimes that you can create a subroutine that actually allocated the array inside the subroutine, and then because D here coming in here was a pointer, it was automatically associated to the D here, and then C here got allocated inside a subroutine. That is something you can do in modern Fortran anyway, so I will show that later here. But if I go into my pointer example here, so I have the same code here, and if I change that one, and if I run this code now, I was hoping for a big string coming up on the screen here, but it didn't when I tried it here. So apparently it handles this here. What you can see here that when I do B11 equals to 0, program receives zigzag segmentation for invalid memory reference. So it will not stop you from doing that, but it will crash.
Meaning that it won't check if the pointer is sort of valid.
No. Yeah, so what can you use pointers for? So pointers actually enable Fortran to become more like other languages, that you can create efficient linked lists, hash maps, binary trees, and you can jump through these structures, and you don't have to fake these structures using index integer arrays. You can actually use real pointers to create these more complicated data structures. You can also have, which is kind of leads to that, so you can have pointers can be contained in derived data types. So you can have, for example, a linked item, for example, that has the next and previous element. You can go back and forth. So that is something you can do in your by using pointers in derived data types.
I sent you this some version
Yeah.
numbers at least.
Oh, should have stopped recording here. Continue. So advanced I/O, we just managed to go through text file basically, and now we will continue with a bit more advanced text files and then also binary files. So it's here. Yes, so list-directed I/O is what we have used up until now. So it uses a special format for reading and writing variables to files. So writing star by star will write files separate with blanks. Complex numbers are written with a parenthesis and as a pair. And strings must be enclosed in string markers when output. And also reading these files back, you will have to have the same format. So for example, here I have I will write a string to a file. I write A, B, and a string, and topping and C to a file. And A is an integer, B is a floating point, string is a string, topping is a logical variable, and complex is a complex value. And you, as I said, to be able to read back a string, you need to enclose it with string markers here. So in this case, I will write out double quote here and close the string with a double quote here. And that's the variables like this. And this will look like this in the text file. So you have 42, 76, 17, 64, hello string. You can see here I have enclosed the string with this. And then I have true or false with either be T or F. And the complex number you can see here, parentheses, and then comma here. So list-directed I/O is the default text reading. And then you can read again, back again here, and then you can do A, B. But string, if you have a string with an enclosed string in your text file, you can just read it like this string. You don't have to do anything special. Topping here will be red. If it's F, it's false. If it's T, it's true. And C here will be red as a complex. So if you run this, it will give you the same output as you wrote out.
And the status code there.
Replace. Yeah. So I think you can do the same thing we did before. You can write the operation. What did we have? You can have action as well. But
actual those ones.
So if there is an existing, sometimes the Fortran is a bit. Let's see if I can go back to. It's a bit. If there are already existing files and you want to write it, you'll kind of complain that there's already a file. So if you want to overwrite, sometimes you need to add this status replace here.
So that will overwrite the file.
Yeah. It ignores any other status and overwrites. Sometimes when it's in different operators, it behaves a bit differently. So I'm not sure why I kept this here.
Old would make sure that the file exists then when they open for read statement.
Yes. Yeah, exactly. We're open. Yeah, but you need to have a file.
Yeah.
Sorry, you caught me a bit off guard there. But
sorry. I just saw those new things that I didn't know.
I think it's to clarify how it should handle the difference when it's reading. If it's already there, it will replace it. I think if you don't have it, it will complain there is already a file and don't overwrite it. So there's a lot of parameters, and so you can see there is all keyboard arguments, and there's a lot of them for the open statement.
I guess so.
Yep, because you don't have objects in Fortran by default, so you need to have a lot of arguments here. Anyway, so that will write out the file, and you can read it back again. And if you want to create these files in another editor, you have to kind of adhere to the same things here to be able to read them back. Namelist I/O is kind of an extension of this, and here you can read and write from a text file where you can name your things in the text file as well. And value names are defined in something called a name list. And the input must consist of named value pairs separated with comma. So we have and name equals to value, name equals to value, dash. You can have arrays, and then you just give them as 1, 2, 3, 4, and 5 with commas between them. And I think we need an example here. So I have all my variables here, number of eggs, liters of milk, kilos of butter, and a list here. And then I have a name list here, which defines for Fortran which variables I want to use in my output files or input files, so when I read. So I just list the same here. Those I want to use when I write the file. And then I can do open for reading. And then I just give name list food. Then it will read all these variables from the file and store them in these variables here. And you can do the same thing. You can write in the other direction as well. Name list food, and I will write the variables to disk. These are specified in my name list, and also in the order that you have them in the name list. Don't I have an example of this? Let's see here. I can do that. So let's see if I can find my... So this is how the file actually looks like. A bit odd. So you have, this is the name list and food. And then you have your variables, number of eggs equals to 1, liters of milk equals to 2, you have a comma, kilos of butter 4, comma, list 1, 2, 3, 4, 5, comma, and then slash at the end. So this is something that has existed for a long time in Fortran, so that's why it's a bit... But it's similar to what you do with JSON files, but in Fortran. You can read them, you can write them, and it will assign the variables. These are the variables in Fortran that will be assigned as well. Then the final format is, we don't care about formatting, we just want to write it down to disk as efficiently as possible. And that is one reason for text files is not very efficient to representing data with high accuracy and also with exactly as it was in memory. So with binary files, you will write the contents of the memory arrays directly down to disk, for example. And you do that using the read statement, but then without the format specifier. So read, and where you want to read it from, unit here, and then the variable. Write, unit, variable. And also to be a bit careful, it's not necessarily that if you write data on one system, that it's actually identical to on another system. So you can't be certain that this is the case. So use this when you want to kind of do a snapshot of your calculations, for example. You can dump it down to disk and read it back again, but don't rely on that this being a very structured file format or something, but it can vary. So for scratch files and temporary files, it's ideal. Direct files access files is also related to binary files. So when you do read and write here, just those are written and read in the same order. You can't jump back and forth to them, but you can that with something called direct access files. So if you need to access a file, data in a file in a random order, but where you have a structure, every data item is the same, you can use direct access files. then you can go to any record in this file and access them randomly. And also, if you change the record size, for example, if you change the derived data type that you store, you can't read the data back. It has to be exactly the same thing, same format as you wrote it. The size of a record can be found using inquiry, so you can query the length of the variable using the inquiry statement. So here is an example. I have defined a derived data type called account. I have a character string, account holder, and a balance. And I create 2 accounts. And then the first thing I have to do before I start using this data type in a file is I have to query the record size. And you do that by inquiry, IO length equals the record size. And then you give an example of the data type you want to store. So in this case, record size will be assigned the size of the account A. And I print it out here. Then you assign the data here. And then you give it access direct here instead. You give it record length, record size. And then you can do write record equals to 1. It will write at position 1, position 2, where you want to store it in the file. So when you have written file and you read it back, you want to kind of move in the file. You can do that using these statements here. You have backspace that will move a cursor in the file one step back. Rewind will go back to the beginning, and end file will move the pointer to the end of the file. So a file pointer is an invisible cursor in your file. Yes. Error handling in file operations. So errors can happen with the open files. You close files, you read files. And this is one of the kind of not so nice features in Fortran, but every of these functions have a special keyword argument which you can specify a line number. That's the only thing when you use line numbers, when you have error handling. Which is, I'm not very proud of this, but this is what it is. So you can compare it to exceptions. So if you have line numbers, they will be exceptions in Fortran. So if you have open and a file doesn't exist, it will go to the line specified in the error statement here. And it goes to 99 here and prints out this error. I hope they will change that at some point. But
And then after doing that, we'll just return.
yeah, it would end the program here in this case.
Oh, so it
because it's
it's really go to statement.
Yeah. Modern Fortran features. So yeah, I will go to kind of the later standards now and just give you some new stuff that has been added to Fortran. So allocatable arrays can be dummy arguments. I showed an example with pointer. You don't need that anymore. So you can do like this. So you can have create array, real allocatable intent out, a comma colon, and then you can allocate it in your array here. And because it's intent out, it will be allocated when that call has been made. So you can create your own allocation routines. So for example, if you want to create an array with a certain content, like once in MATLAB, for example, you can do it like this. You can create once, and then you can create the array in the function and return it back. You can also have allocatable arrays as return values from functions. I have some issues with this before, that not all compilers compile this code, but it is possible to do a function like this, a equals to create vector. But I haven't, I'm not really sure which function. Let's see here, I can just exactly run this. Yeah, so it seems to be like at least Fortran 13.2 will compile this. But I know that there are some older compilers that will not compile it, so this is a relatively new feature of Fortran. But it makes a really nice syntax here. to be able A equals to create vector, but now that is not allocatable. How did that work? Okay, it worked. Yeah. So it's nice syntax. And it's possible now as well.
So what if you remove allocatable?
Sorry?
What if you remove allocatable blocks?
I don't think now then you can't have this. I think this is this hides the.
Creating that.
Yeah, but I think it's. I'm not sure. I think it returns the same. This one here. I'm a bit confused here, but I think it's. Yeah, but at least this should work. We can try to do. Let's see here, a bigger one, just to make sure allocatable. Then we do 200. Yes. So now this is allocated in here and returned out here, and the size is correct. But if we do, let's see if we do like this, then we can test. Yeah. Now it hides the allocated variable that is returned.
So it is deallocated inside of
Yeah, it's deallocated inside this one here because it's not used. Or at some point it's deallocated.
What does line 7 mean?
Good question. I really. It could be that it tries to assign that one because you do allocate vector.
It's not the definition of the variable.
Sorry.
On that view line, aren't you defining the variable?
Well, it wasn't redefined, and that's my issue.
So if I so this is allocatable. That is in a kind of a empty array, which is not allocated yet. And if I remove allocate and I put A20, then it's allocated on the stack.
So define, because that's the definition, right? You're defining the variable or the vector. The variable A as a vector of 20 elements.
Yeah. But the thing is, I'm not sure what happens here. So you have a fixed array,
Yeah.
and then you assign this. This should assign this one here.
But now it's not fixed, but in the previous
It's not
version.
possible because it's not allocated. It's not allocatable.
Exactly. That's. I thought I would get an error like if I do that. This.
So now, what's the meaning of line 7? That's what I don't
Yeah.
really understand.
No, I have to look at that. I'm a bit surprised about this.
No proper return on the function, is it?
So what I do here is I assign. So create vector is allocatable, real allocatable dimension colon.
Yeah, but that's
And that is assigned here, basically. When you create vector here,
it's allocated there.
you allocate create vector here,
Yes.
and that should be
returned, right?
yeah, and then it's should be this should be equivalent, but it's not. So
It should be equivalent to the return of the function.
the question if what no. I need to check this. I can't answer it right now, but it's it could be it overwrites A and with something. I need yeah.
That's good.
It could be that that A20 becomes the pointer of the allocated array, and it just fills that up. So yeah. If you get a solution, you get back to me. Let's see here. Also, something that was really recently as well is that before you couldn't have allocatable data types in your derived data types. Now you can. Before you had to have pointers. And now you can have allocatable inside. It sounds like a really obvious thing to have, but it was not until Fortran 2003 or something that you could do this. So these features are kind of old, but anyway, it's newer. Submodules is also something that is kind of new. Is if your modules get large, you can actually divide them up in separate modules with just a single name, but the implementation is divided up into multiple modules. So you can have like submodules point A that will belong to this point here. So it's just a way of dividing up into more source code files. This one is important, I think. This has always been a problem with Fortran, that there was no real clear distinction between the data types in Fortran and C. And C in Fortran program is kind of important. You often mix these languages together. You mix Python and Fortran, and Python is implemented in C, so C in Fortran is important. There is a new built-in module called ISO-C binding. I think I covered it a bit before. And it contains the definitions of all the C data types mapped to Fortran types. So as I say, you can have C int, C float, C double, and so on. You can also have suffixes like this. And that means a lot, especially when you're defining subroutines that you want to link together with C. You can use these data types and you get one-to-one mapping directly. Another thing that also comes with this module is that in Fortran, everything is passed by reference. And in C, scalars are passed by value, arrays are passed by reference. And there wasn't a way of doing that in Fortran before. So in Fortran, you couldn't declare a subroutine with passed by value for the variables, the parameter, our arguments. But in modern Fortran, you can do that. And you can actually add an attribute to your variable declaration called value, which means that you can link directly with C. I didn't have an example here. I got it here. Okay, I didn't have it. Okay, but you can, you can add a value to your subroutine. Let's see if I have it in my. Well, I didn't have that example either. Okay. Anyway. Another thing that also is available now is, which also was not available before, is access to the computing environment. So if you, for example, wanted to query an environment variable in Fortran, you couldn't do that in Fortran 7.7. Also in Fortran 90, it's only the latest version you get these commands. So get environment variable, so you can query any variable in your code. Command argument count. That is also something that hasn't been part of the standard. So now you can actually query command line arguments of your code in a standardized way. There were some extensions to other compilers that could do this, but this was something that has been added as well, which makes Fortran kind of be able to compete with C and C++ as well. And now I think we have an interesting discussions here today, but I think I will move this to the next lecture, how you build stuff as well. It's available in the slides, so you can continue afterwards here, but I will only get to half of this today, so that's why I think we'll skip that to the next lecture. Okay.